Dear students, I am Dr. Harel Thomas, Professor in Applied Geology, Department of Applied Geology, Dr. Harisingh Gour, Vishwavidyalaya, Sagar. Today, in this course, I will deliver my lecture on silicate mineral classification part 3. It is just for revision of your undergraduate course because mineralogy is a backbone of petrology. In this lecture, I will proceed under the following heads: phyllosilicates and tectosilicates with example, etc. In my previous lectures, I have covered sorosilicate, cyclosilicate and inosilicate. I believe it will be useful for you before embarking upon the main topic of the paper, that is metamorphic petrology and thermodynamics. This group is characterized by seat structures. The 3 oxygen of each tetrahedra are shared with adjacent tetrahedra to form extended flat seats extended in 2 directions, remaining apical oxygen points towards you. This apical oxygen generally bonds with others octahedrally coordinated cations. Different stacking arrangement of tetrahedral seats and octahedral seats, along with the type of cations that occupies the octahedral site, allow for the variety of phyllosilicates that occur in nature. The SiO ratio is 2:5 and it is fundamental unit in all micas and clay structures. The seat form hexagonal planar network and responsible for phyllosilicate, phyllo equal to seat. Octahedral varieties includes dioctahedral. Cation in octahedral seat is trivalent +3, usually Al +3. The -6 charge from the anion is satisfied by only 2 trivalent cations. Therefore, 1 out of every 3 cation site is vacant. Each O or OH is bounded to 2 cations. Trioctahedral cation in octahedral seats are divalent +2, usually Mg or Fe +2. The -6 charge from the anion is satisfied by the 3 divalent cations. so all cation sites are filled with each oxygen or OH is bounded to 3 cations. Example of phyllosilicates, mica type or 10 angstrom type. In this type, there is a layer of octahedral coordinated cations sandwiched between two identical tetrahedral layers with apex of tetrahedral pointing towards each other. The repeat distance is 10 angstrom along C direction, have a T O-T stacking patterns, tetrahedral seats for every 1 octahedral seats. Alkali mica, muscovite, white mica or potassium mica, KAl2, AlSi3O10 OH twice. Paragonite, soda mica, NaAl2, AlSi3O10 OH twice. Trioctahedral mica, lepidolite, lithium mica, Kli2, AlSi4O10 OH twice. Zinwaldite, lithium mica, potassium under bracket lithium, iron bracket close AlSi4O10 OH twice. Phlogopite, magnesium mica, Kmg2 AlSi3O10 OH twice. Biotite, black mica or MgFe mica, KmgFe thrice AlSi3O10 OH twice. Phyllosilicates, kaolinite type or 7 angstrom type, 1:1. In this, one tetrahedral layer is shared with an octahedral layer. The resulting structure is 2-layered and repeated distance is 7 angstrom, have a T-O stacking pattern, 1 tetrahedral seat for every 1 octahedral seat. Dioctahedral kaolinite Al2 Si2O5 OH4. Trioctahedral talc soapstone Mg2 Si4O10 OH twice. Serpentine Mg3 Si2O5 OH4. Phyllosilicate, chloride type or 14 angstrom type. It consists of 2 octahedral layer and 2 tetrahedral layer and repeated distance is 14 angstrom. Chloride Mg5Al, AlSi3O10 OH8. Tectosilicate or silicate or framework structure. In tectosilicate, tecto equal to framework, SiO4 tetrahedra share all its corner with other tetrahedra, form a 3-dimensional network in which SiO ratio is 1:2. The various form of silica SiO2, namely quartz, tridymite, cristobalite, have the network arrangement in SiO4. The positive and negative charges are balanced. In silicate of this type, structure of silicon is partially replaced by Al plus 3 and the combination is SiAlO twice. The substitution of Al plus 3 for Si plus 4 require additional positive ions in order to restore electrical neutrality. For example, orthoclase KAlSi3O8, albite NaAlSi3O8, naphthalene NaAlSiO4, etc. Silica group, quartz SiO2, feldspar group, orthoclase KAlSi3O8, microcline KAlSi3O8, albite NaAlSi3O8, plagioclase series NaAlSi3O8 to CaAl2 Si2O8. Feldspathoid group, lucite KAlSi2O6, naphthalene NaAlSiO4, sodalite Na8AlSiO4 6Cl2 Zeolite group, Hollandite CaAl2 Si7O18 6S2O, Stabilite CaAl2 Si7O18 7S2O, Lomentite CaAl2 Si4O12 4S2O, Analcine NaAlSi2O6 S2O, Natrolite Na2Al2 Si3O10 2S2O. Dear students, today we have discussed in this lecture about the phyllosilicates and tectosilicate with example etc. Hope it will be useful for all of you before embarking upon the main topic of the paper, that is Metamorphic Petrology and Thermodynamics. I believe this lecture was useful for you to revise your mineralogy, which is important to understand the petrology. For further studies, please read the books and references given in the text. Thank you very much.